Detecting an atmosphere around a rocky, Earth-like exoplanet is one of the big dreams of modern astronomy. But right now, most of the planets we can study in detail are orbiting M dwarf stars. Compared to the Sun, it's smaller, cooler stars whose planets tend to have very narrow orbits and often be tightly locked to the star, like our Moon to the Earth. That means that one side of the planet is permanently facing the star, while the other has permanent night. And that has a surprising consequence. It may be extremely difficult for these planets to hold on to their atmospheres. In a recent paper entitled Atmospheric Collapse and Reinflation Through Impacts for Terrestrial Planets Around M Dwarfs, which is led by Prune C and co-authored by Lars Buchhave from DTU Space, the National Space Center here in Denmark, together with collaborators in the US, the astronomers look at a very specific version of exactly the problem of holding on to an exoplanet's atmosphere. On these tightly locked planets, if the atmosphere becomes too thin, it can no longer efficiently transport heat from the day side of the planet to the night side, and the night side cools down, and eventually the main atmospheric gas, in this case carbon dioxide, condenses out onto the surface of the planet as ice. Once that happens, a runaway process takes over. The thinner the atmosphere becomes, the less heat is transported, the cooler the night side gets, and the more the gas freezes out. The atmosphere doesn't just thin, it collapses entirely onto the surface of the planet. But here's the key point of the paper. The collapsed atmosphere isn't gone. It's stored as a reservoir of ice on the night side of the planet. And the reservoir can, in principle, be brought back to life, so to say. But what mechanism could do that? The authors focus on meteorite impacts. Methodologically, they treat the planet as a two-state system. Either the planet has an atmosphere or the atmosphere is collapsed and stored as ice. So what do they find? Even moderate-sized impactors around 5 to 10 kilometers across can be enough to temporarily regenerate an atmosphere if they occur at realistic rates. And that leads to an interesting conclusion. These planets may not evolve smoothly. Instead, they may spend a large fraction of their history switching between collapsed and reinflated states. For some specific exoplanets observed using the James Webb Space Telescope, the authors find that up to 50 to 80% of the time, a planet could have a transient atmosphere created in this way. There's also an important insight about the atmospheric laws in this study. When the atmosphere has collapsed, the volatile elements of the atmosphere are protected on the surface, especially during the early, highly active phases of the life of an M dwarf star. So perhaps counterintuitively, the collapse may in fact help preserve the ingredients needed to rebuild an atmosphere later. The broader message is quite powerful. Exoplanet atmospheres may not evolve gradually. They may be episodic, unstable, and driven by external events like impacts. And that means that when we observe an atmosphere, or if we don't, we may just be catching the planet at the one moment in a much more dynamic history where this is the picture we get. Check the link to the paper in the description below, and remember to like and subscribe.